This video is another example of the paired t-test. The following table lists SAT scores before and after a sample of 10 students took a preparatory course. Is there sufficient evidence to conclude that the preparatory course is effective in raising test scores? Use a level of significance of 0.05. So we have measurements taken on the same subject, so we have dependent samples. This is a typical before and after situation. And we're assuming that the differences are normally distributed so that the paired t-test can be used. So for example, this particular student, the SAT score before was 1180, and then after the preparatory course it was 1200. This subject before was 830, but after the preparatory course the score went down. So the question asks, is there enough evidence to say that this course is effective in raising the SAT test scores? We need to write the null and the alternative in terms of the parameter mu sub d. To get that, we can first compare the mean before and the mean after. Now, if we want to raise SAT scores on average, we would want this mean after to be greater than the before. Sometimes setting up the null and the alternative for a paired t-test is the hardest part. So moving mu sub a over to the left side using subtraction, we'll have 0 on the right, and we can rewrite this difference as mu sub d. Because this doesn't contain the case of equality, this will be the alternative. So the alternative is that mu sub d is less than 0, and the null will be mu sub d is equal to 0. This is a case of no difference between the before and after. So if we end up being in favor of the alternative, then we could say that the preparatory course is effective. Okay, so the alternative is essentially the claim in this case. The standardized test statistic is d bar, the sample mean of the differences, minus mu sub d over s sub d over the square root of n. This mu sub d comes from the null and the alternative, and that's just going to be 0. N is the number of pairs of data, and we have 10 students, so n is equal to 10. We just need d bar, the sample mean of the differences, and looking at our order of subtraction, we want to subtract the after from the before and get a new row or column of data, which will be the differences for each before and after. And we also need that standard deviation for the differences. Now, rather than having to do this subtraction, the before minus the after individually for each one, I went ahead and put the befores and the afters in list 1 and list 2 respectively, and I can have the calculator do the subtraction for me. I'm going to arrow over to list 3 and then enter so that the cursor is at the bottom of the screen. And then I'm going to take list 1 minus list 2 using my second and number keys to get those lists. Press enter, and then the calculator will create that column of differences for you. So we need the mean and standard deviation for that third list. To do that, go to your stat menu, over to calc, one variable statistics, and you want it for that new list that was created. D bar will be -11, and S sub D is the sample standard deviation for that column, and that's going to be 20.248. So inputting into this formula, I'll have -11 minus 0, so this is going to be a negative standardized test statistic, over 20.248 over the square root of 10. Inputting that into my calculator, .248 divided by square root 10. You know what? I think I would like parentheses around that, just so that the calculator treats that as the entire denominator expression. The standardized test statistic will be -1.718, rounding to 3 decimal places. To get the critical value, you'll need to go to the t-table. So sketching the t-distribution, and this is a lower tail test. So I'll have one lower tail area of rejection. We're using a level of significance of 0.05. And since our sample size is 10, or the number of pairs of data is 10, the degrees of freedom will be equal to 9. The t-table gives the positive values, the upper tail values, but by symmetry, the bottom or the lower tail will just be the negative version of that. So reading down to 9 degrees of freedom over to 0.05, that would be this column. The standardized test statistic is -1.833. If you have an inverse t-distribution in your calculator, you could use that and put in a cumulative area of 0.05 with 9 degrees of freedom and get the same value. So the standardized test statistic, -1.718, is not further to the left of this critical value. It's somewhat close though, but it is in the fail to reject region. So if we're failing to reject the null, to answer the question, is there sufficient evidence to conclude the preparatory course is effective? To answer that, there is not sufficient evidence to conclude that the preparatory course is effective, because we're failing to reject the null, and the null is the statement that there is no difference. To get the test statistic and p-value directly from the calculator, we can do a little bit of a workaround because the paired t-test is not an option under the stat and test menu. But since we created a third list of differences, we can run a single sample t-test on list 3. Going to the stat menu, over to tests, option 2 is the single sample t-test. I want to leave it as data because I'm using that column of differences. My null statement is that there is no difference, so I want to leave this as 0. My data is in list 3, and I need to change this alternative to be a lower tailed test to match the alternative in the problem. And then calculate. You'll see that the standardized test statistic rounded to 3 decimal places is the same, and the corresponding p-value is about 0.06. So if a p-value of about 0.06 and my level of significance is 0.05, The p-value is greater than or equal to that, so I know my decision at this level of significance is to fail to reject the null. But if our level of significance was 0.10, then the decision would change. The p-value would then be less than 0.1, and the decision would then be to reject the null. So it is possible to fail to reject at one level of significance and reject at another.